Is Yuan Zhang. Yuan is a rising fifth-year PhD student at the University of Michigan, and his research interests are in providing performance isolation and quality of service in data center networks. Unfortunately, Yuan couldn't be with us today, and so the presentation is going to be a recorded video followed by online Q&A. We are ready. Thank you.
My name is Yuan Zhang, and I'm from the Symbiotic Lab at the University of Michigan. Today, I'll be talking about our work, Aequitas, which is an admission control for performance-critical RPCs in data centers. This is a joint work with Google. With the increasing popularity of disaggregated storage and microservice architectures, RPCs now generate most traffic in data centers. Indeed, we observed that RPCs generate more than 95% of application traffic in Google production data centers. It is not surprising that nowadays, developers view RPC performance as key indicator for their application performance. Therefore, it is important to understand that what can affect RPC performance. Well, it turns out that RPC performs well most of the time, except for the case of network overloads. Network overloads can happen when multiple applications surge in their demand in the data centers. There are two takeaways we learned from our production incidents. First, network overload can sometimes surge to as high as 8x than the usual load. And second, the network component of the RPC latency can dominate the latency spikes, leading to unavailable service. Now, how can we improve RPC performance in this case? It is important to note that during network overloads, the demand is greater than system capacity, so it is not possible to improve everyone's performance. Instead, our goal is to provide network latency SLOs for those important RPCs. To identify which RPCs are important, we classify our application traffic into 3 priority levels based on different SLO requirements. Performance-critical RPCs are latency sensitive with microsecond scale tail latency SLOs. Non-critical RPCs are usually super sensitive with less stringent SLOs. Best efforts RPCs, on the other hand, have no SLOs as long as they complete. Now, before we talk about our actual design, let's first look at why existing solutions cannot achieve this goal. One popular choice of handling traffic with different priorities is to use priority-based approaches. Size-based schemes such as shortest job first or shortest remaining time first are good at minimizing the average RPC latency. However, in our cluster, we find that RPC size is not fully correlated with RPC priorities. Using such scheme will prioritize short, unimportant RPCs over large, important RPCs. Moreover, these schemes are not readily deployable due to their hardware complexity. Another approach is to strictly apply RPC priorities using strict priority queuing. This approach is straightforward in priority mapping. However, it also incentivizes everyone to use the highest priority. Plus, SPQ is known to have starvation issues. One solution that gets widely deployed by many cloud providers, including Google, is weighted fair queuing. There are 2 reasons why people prefer weighted fair queuing. First, its bandwidth sharing properties enables an easy mapping from priority classes to quality of service queues supported by weighted fair queuing. And second, it is available in most commodity switches, making large-scale deployment very easy. Using weighted fair queuing also comes with 2 constraints. First, QoS classes are not really associated with SLOs. And second, the priority mapping is coarse-grained. A common model used in practice by many cloud providers is to map the entire application traffic to the same QoS level. This will create misalignment between RPC priorities and network QoS levels. The following figures show the QoS distribution of the best effort RPCs in our cluster. Because of the coarse priority mapping, we can observe that over half of the BE RPCs are using higher QoS levels than necessary. Such overloads of low priority traffic using high network QoS can cause other high priority traffic to suffer. Now, to overcome these constraints of the existing approaches, we built Aequitas. Aequitas aims to achieve the following design objectives. First, we want to improve the current coarse-grained priority mapping with a more fine-grained approach. And second, we want to better manage the distribution of traffic among QoS levels to provide better isolations for high priority traffic. Here, the distribution of traffic among QoS levels is a key concept in Aequitas design, and we call this QoS-Mix in our paper. And I'll be referring to this term many times in the following slides. Our last objective is to provide guaranteed SLO for our important RPCs. Now, with these objectives defined, let's look at Aequitas' actual design. One key insight in our design is that weighted fair queuing is actually an excellent building block to provide latency SLOs as long as the QoS-Mix is explicitly managed. This key insight is based on our theoretical analysis on weighted fair queuing delay bound, which I'll describe next. To perform the theoretical analysis, we use the following approach. First, we define a traffic arrival model with average load and burst load. And then we apply network calculus to solve for the delay bound with different service curves as the QoS-Mix changes. We have a detailed derivation of these delay bound equations in paper, but today I'll show you how the delay bound looks like using an example with two QoS levels. Here in the figure, we have the vertical axis representing the delay bound and the horizontal axis representing the QoS high share. A 20% QoS high share in this case means that 20% of the traffic is assigned to QoS high, and the remaining 80% of traffic is assigned to the other QoS level, which is QoS low. There are two takeaways in this example. First, the QoS-Mix can affect the delay bound in both QoS levels, and we can observe there are different regions of delay bound as QoS-Mix changes. And second, as we keep increasing the QoS high share, we will hit a priority inversion point where the delay bound of the QoS high class is greater than, becomes larger than the delay bound of the QoS low class. This implies that we need to select our QoS-Mix before this priority inversion happens, as indicated by the shaded area in the curve. In the paper, we call this an admissible region. Now, if we draw a vertical line to represent a selected QoS high share, we can find a delay bound for QoS high. The idea here is that if we call this delay bound to be the SLO for our QoS high, then as long as we stay at this desired QoS high share, we'll be able to provide SLOs for our QoS high class. Similarly, moving on to the 3 QoS case, again, we can insert a vertical line inside the admissible region and then set the corresponding delay bound to be the SLO for QoS high and QoS medium class. Again, as long as we can control our traffic to stay at this desired QoS-Mix, we'll be able to provide latency SLO guarantees for our important RPCs. This is essentially the key design ideas of Aequitas. In a high level, Aequitas has achieved this key idea in a 2-step approach. First, it aligns priority classes with weighted fair queuing QoS levels at the granularities of RPCs. And second, it explicitly manages QoS-Mix by admission control. Let's first look at the first step, which is priority mapping at RPC level. When applications issue an RPC, each RPC will carry an RPC priority, which gets mapped to a requested QoS. Here we do a one-to-one mapping from PC RPCs to QoS high, NC RPCs to QoS medium, and BE RPCs to QoS low. Note that this requested QoS level is not the final QoS we admit into the network. Instead, Aequitas decides an admitted QoS level based on this given requested QoS level based on its admission control in order to adjust the QoS-Mix. Next, let's look at how Aequitas performs this admission control. We adopt a probabilistic approach when admitting RPCs. The admission decision is made based on an admitted probability, or p-admit. Based on the value of this p-admit, Aequitas either admits the RPCs with this requested QoS level, or it downgrades the RPC to the lowest QoS level. Here, the lowest QoS level has no SLO guarantees and serves as a scavenger class. When a QoS downgrade happens, Aequitas also notified the applications such that they had freedom to update their RPC priority distribution in their applications. Next, let's look at how our admission control maintains and updates this admit probability. Our admission control works in a distributed way. At each end host, the admit probability is maintained on a per source, destination, and QoS basis. At the same time, Aequitas also collects measurements of RPC network latency on the same source, destination, and QoS basis. The value of p-admit is updated using a simple AIMD scheme. On each RPC completion, if the latency measurement is within the SLO target, this implies that we are still below the desired QoS share, and we can admit more RPCs by increasing the value of p-admit. On the other hand, if the latency measurement is above the SLO targets, given the RPCs of the requested QoS level, then this implies that we have admitted too many RPCs on this QoS level, and we need to decrease our p-admit. The reason why we use the AIMD scheme is to provide fairness such that a tenant sending too many high-priority RPCs will not cause QoS downgrades for other well-behaved tenants. Our admission control algorithm also handles different RPC sizes, and you can find more details in our paper. Next, before we move on to the evaluation results, let's do a quick recap to see how Aequitas works in a high-level system diagram. When applications issue an RPCs, we map its RPC priority into a requested QoS level. At the same time, Aequitas admission control is sitting on the RPC stack and collects RPC latency measurements. Based on the per QoS SLO targets, it computes an admit probability to decide whether this RPC gets admitted or downgraded. Finally, when this QoS downgrade happens, it sends back an application and notification. Next, let's highlight some evaluation results from the paper, with a focus on providing SLO guarantees for important RPCs. You can find more experiments in the paper, including a large-scale evaluation with production RPC sizes. In the selected experiment, we use a 33-node setup with all-to-all traffic pattern. We fix the RPC size to be 32 kilobyte, and there are 3 QoS levels with QoS weights of AS24:1. Traffic arrives at an average load of 0.8 with a burst load of 0.4 with Poisson arrival patterns. To start, we define a desired QoS-Mix of 25% on both QoS high and QoS medium, and 50% traffic on QoS low. We set the SLOs for QoS high and QoS medium using the tail latency measurement under this desired QoS-Mix, which is 15 and 25 microseconds. Now, we pick an input QoS-Mix. Before applying Aequitas, this input QoS-Mix will cause bad tail latencies and miss both SLOs for QoS high and QoS medium. After applying Aequitas, Aequitas is able to converge this input QoS-Mix back to the desired QoS-Mix, and it can achieve the SLO requirements for both QoS high and QoS medium. We observe that Aequitas can improve the tail latency across all 3 QoS levels by up to 5x in this experiment. Also note that by closely converging back to the desired QoS-Mix, Aequitas is able to maximize the number of traffic and the amount of traffic emitted on both QoS high and QoS medium within their SLO requirements. In conclusion, we talk about that RPC performance is critical for modern data center applications, and we show that by using a combination of admission control plus weighted fair queuing, Aequitas is able to provide latency SLOs for important RPCs during network overloads. Our code is open source on GitHub, and thanks for listening, and I'm happy to take questions.
Thank you, Yuan. Do we have a live? Yes, we have Yuan live. Any questions for Yuan? There's a mic over there. Questions? I can start with a question while the audience warms up. Yuan, I was wondering if your approach can support per application or even perhaps per tenant SLO guarantees?
Yes, actually, because we measure, we measure the RPC latency measurements, and also we maintain the admit probability on a per RPC connection. So basically, you can make pertinence to use a particular RPC connection on a per source destination and QoS basis, and use that to provide performance guarantees on a payment basis.
I see. That's cool. Thank you. Any questions for Ewan? All right. Let's thank Ewan once more. Oh, pardon. Forgive me. I can't see. Please.
Thank you for a great talk. So how do you translate this QoS on the service on the network itself? Meaning, how do you signal to different switches on the way not to drop specific packets? Do you use traffic classes or something else, or you do some sort of a translation?
Yeah, good question. So basically, we mark. So each packet will carry. So we make one of the header fields to carry the QoS information, and inside the switch, we also use like buffer carving. Where we have, so for each priority classes, there is a certain cap of packets that can be held on the buffer. So situations such as where you have too many like low priority packets, it will not overflow or take many spots for other high priority packets based on this switch buffer carving.
All right. Any questions? All right. Now we can thank Ewan one more.